Hello, I am Ghinwa, and I'm gonna share with you a small video explaining LTE radio interface and how to calculate physical bitrate in downlink and in uplink. So first, let us talk about LTE Air Interface. For the downlink, orthogonal frequency division multiple access OFDMA was selected. For the uplink, single carrier frequency division multiple access SC FDMA was selected. Orthogonal frequency division multiplex is a multi-carrier technology subdividing the available bandwidth into 15 kHz subcarriers. So, OFDMA and downlink. Multiple users receive information at the same time, but on different parts of the radio channel. Each user is allocated subcarriers in group of 12, known as physical resource block. In this example, we can see 3 users. User 1 in blue is allocated 7 resource blocks, each resource block consisting of 12 subcarriers, as we said. User 2 is allocated 4 resource blocks. User 3 is allocated 4 resource blocks on the available bandwidth. In uplink, we have similar principle, but UE is allocated consecutive resource blocks. From the UE's perspective, the frequency allocation is seen as a single carrier, thus giving the term single carrier frequency division multiple access. OFDM enables operators to deploy LTE in different regions with different frequency bands and bandwidth available. In fact, we have 6 available bandwidths starting with 1.4 MHz up to 20 MHz. For each bandwidth, we have a corresponding number of resource blocks ranging from 6 to 100. Knowing that one resource block consists of 12 subcarriers with 15 kHz spacing. So each resource block is equivalent to 180 kHz in the frequency domain. To be noted that LTE is developed to support both paired and unpaired spectrum. Now let us talk about the time domain. In LTE, we have a 10 millisecond radio frame subdivided into 10 subframes. Each subframe lasts 1 millisecond and consists of 2 slots. Each slot lasts 0.5 millisecond and is divided into 7 OFDMA symbol in the case of normal cyclic prefix. One subframe will carry 14 OFDM symbols. In brief, radio resources are defined in the time and frequency domain and divided into resource blocks. A physical resource block consists of 12 consecutive subcarriers during 0.5 milliseconds. User is typically allocated 1 millisecond of time, so 2 slots and 2 consecutive physical resource blocks. Each slot is subdivided into 7 OFDM symbols, so 1 millisecond will be subdivided into 14 OFDM symbols. And since we have 12 subcarriers, we will have 12.14, so we have 168 symbols that can be transmitted during 1 millisecond. Now I'm gonna show you how to calculate LTE throughput in downlink and uplink. But first, note that throughput will vary according to channel bandwidth and the functionalities used, such as adaptive modulation and MIMO and other functionalities. LTE supports adaptive modulation, so E node B can select QPSK, 16 QAM or 64 QAM. E node B will select the appropriate modulation depending on the radio environment. So based on estimation of the quality in uplink and downlink, E node B will select either QPSK or 16 QAM or 64 QAM. If we have poor radio, E node B will use QPSK, so 2 bits per symbol. In a good radio environment, E node B will select 64 QAM, and we will have 6 bits per symbol, yielding the highest throughput. In LTE, MIMO, multiple input, multiple output, is included in the standard. In the first releases of LTE, the E node B is equipped with 2 transmit antennas and UE with 2 receive antennas. In a poor radio environment, both E node B antennas can send same data to improve reception at the UE. So we talk about transmit diversity. In a good radio, antenna A and antenna B can send different data streams to the UE. Throughput will be increased, and we talk about spatial multiplexing. In this example, we have 2 transmit antennas and receive antennas. So we have 2 layers and the throughput is doubled. This is an example on how to calculate throughput and downlink. As mentioned earlier, we have 6 available bandwidth, and for each bandwidth we have a corresponding number of physical resource blocks. Suppose bandwidth is 20 MHz, so we have 100 resource blocks. Each resource block is equivalent to 180 kHz in the frequency bandwidth. Now in the time domain, we have a 10 millisecond radio frame consisting of 10 subframes. Each subframe carries 168 symbols. So we have 168 symbols times 10 subframes times 100 resource blocks equals 168,000 symbols in 10 milliseconds. So in 1 second it will be 16.8 megasymbols per second. Now assuming that the modulation used is 64 QAM, we have 6 bits per symbol, so we multiply by 6 and we get 100.8 megabits per second. Considering we have MIMO with 2 layers, throughput will be doubled and we get 201.6 megabits per second. Of course, user bitrate will be less than 201.6 megabits per second due to signaling and adaptive coding overheads. Same idea in uplink, but note that in first LTE releases, UE didn't support 64 QAM nor MIMO. We have 6 available bandwidth and their corresponding number of resource blocks. In this example, we take 20 MHz, so we have 100 resource blocks, and we have 168 symbols in each subframe, and we have 10 subframes. Same calculation, we get 16.8 megasymbols per second. Using 16 QAM, we have 4 bits per symbol and we get 67.2 megabits per second. As in downlink, the user bitrate will be less than 67.2 megabits per second due to signaling and adaptive coding overheads. Note as well that here downlink and uplink calculations are for FDD. For TDD, downlink and uplink throughput calculation will depend on the configuration of the subframe. We have 7 different TDD configurations within the 10 millisecond radio frame. Thank you for watching, and please remember to share our video and to subscribe to our channel.